Alright, we're going to learn, use what you have learned the last 6 or 7 lessons to solve some practical problems involving uniform and non-uniform distribution. Alright, we're only looking at discrete random variables at the moment. Next semester, we'll be looking at continuous random variables. Alright, so we're just going to solve some practical problem. I'm not going to go through every single thing again, but I'm going to should make sure that you know what I've taught you. Alright? Now, you have to be prepared to combine all the knowledge and skills of discrete random variables you've learned so far, either within or outside the context of the practical problems. So in any case, where the random variable is not defined, be sure to clearly define it. Alright? You must make sure that you define it. Now, let's start off with the first one. A fair spinner consists of 10 equal sectors, each numbered with a digit 0 to 9. Now this one, I've defined it. Let x be the number on the sector on which the spinner lands. Can you determine the distribution of x? You should be able to do it. You know that this should be, it says that there's a fair spinner. So if it's a fair spinner, the probability of it landing on 0 will be 1 over 10, landing on 1 would be 1 over 10, and so on and so forth, right? So therefore, you know that x is uniformly distributed. So we can write x, it's uniformly distributed as in 10. So you've got 10 elements in there, or if you like, you can write it this way. I prefer the first way, which is x. It's uniformly distributed, 10 of them. Alright, so, and it's you have to describe it as uniformly distributed. That's all you need to do. So another spinner is created such that the number are defined by y equals 5x plus 2, where y is the number on which the new spinner lands when spun. You now need to list the number showing on the new spinner. So you know that y equals 5x plus 2, so it's 5 times 0 plus 2, and so on and so forth. Now, you should be able to use your knowledge of y equals mx plus c. Find the first number, straight away you'll be able to do the others. 5 is the radian, yeah? 2 is the y-intercept, which is x equals to 0, right? So straight away you can write down 2, then 7, 12, 17, without using your calculator. Yeah? So think about what you have learned previously, and then you should be able to calculate the mean and variance of y. Expected value, or the mean, is just 9 plus 0, a plus b divided by 2. The two extreme numbers divided by 2, which is 4.5. And k in this case is 1. So it's therefore k times n squared minus 1 divided by 12. K is 1 because it's 0 to 1 to 2. No, sorry. This is y.
Yeah,
so my fault, this is EY. So I started with x first. I worked out x and y first. X first before I go on y because I was going to use the transformation.
What's
my fault?
5 times 4?
I saw the wrong thing. So EX
20,
and
20.
variance of x. Now EY. EY will just be 5 times EX plus 2.
4.
Or you can use 2 plus 47 divided by 2 is the same as well. And then the variance of x is just 5 squared times EX. Of y is 5 squared times EX, which is 206.25. Sorry, I was looking at x, not y. So I started with EX first, so that I can use the transformation and go from E to y. Alright? This is, you can, if you want, use the variance of y and just calculate it with all the numbers.
Yes.
I thought, to me, personally, I think it's easier to start off with EX, then you transform it. Because you're only dealing with one number rather than 2 or 3 or 4 or 5 numbers. Yeah? So it makes life a little bit easier when you do things like this. Calculating EX because K is 1, it's probably a little bit easier than the one. Alright, where the K is 5. You got to work out all the numbers, whatever again. You can do that if you want to. I don't mind. Alright?
Didn't know the E yet. For a uniform distribution,
See,
there's a formula. So it's like so you do the intervals. No, intervals at the start.
Alright, example 2. Now,
So
this
equal
one,
between each thing.
it's
1, 2, 0, 1, 2, this is 1.
slightly different. I want you all to focus this for a while.
Yeah.
Everyone, listen.
Yeah.
I've been looking at discrete random variable where all the x's are just integer, correct? Here is all dealing with money. And it's like something like 250, 350, 375. It's a discrete value. There's nothing in between, but it's not an integer. It's still consider it as discrete random variable because it's discrete. You can only, in this case, you can either win certain amount of money, lose certain amount of money. That's it. Alright? So it's discrete. Or you want to think about it as cents, 250 cents. Then that is integer. Alright? So here, a game of crazy dice costs $2.50 to play, in which the player roll a pair of fair 6-sided dice. If both the dice show a 6, the players get back $12.50. If both dice show a prime number, then the players get back $5. Otherwise, the player, how did I type it? Player loses. All right. So let's have a look at what I did. All right. So I started off with doing this. All right. And I just realized that I made a mistake in my solution already.
Yeah.
Doesn't matter. The answer is the same. I just need to change something, that's all. So let's start off looking at the first bit. The first bit says that if both dice shows a 6, the players get back $12.50. Right? How much would the player win? 10, because it's $12.50, take away $2.50, 10. Alright? So, what you would get is, if I construct this, I will just fill that in as $10. That is the one and only one that you will win $10. Right? There's no other places that you can win $10. Correct? Yeah? So that's it. The next one, thinking about a prime. If both dice shows a prime, the player gets back $5. So how much do they win? $2.50. Alright? This is where I made a mistake. This should have been prime, and prime. So just have to move that across, that's all. My fault. Alright? So that bit here, that should be $2.50 here. $2.50, and the rest are $2.50. Alright? This one's not there, and this one's not there. Alright? So it's clear that you can see one of them is $10. I've got 9, which is $2.50. Correct? Agree? Because if the both dice show a prime number, 1 and 2 and
So 1's not
3.
prime.
No, I've got it wrong. Sorry. 1, anything to do with 1 is not there.
Yeah,
It's totally my fault. Alright? It shouldn't be there. So it's between 2. 2 is a prime, 2 is a prime. That bit here. 2 and 3 is a prime. 2 and 5 is a prime. Alright? 3 and 5 is prime. 3 and 2 is a prime. 3 and 3 prime. 5 and 5 prime. 4. No. 5 and 2 is a prime. 3 and 5 is a prime. Yep, that's it. That's better. Alright? It's my fault.
Not 5.
5 and 5 prime. 5 is a prime, 5 is a prime. 3 is a prime, 3 is a prime. Alright? So ignore this. Ignore that bit there. Alright, my fault. I'll change the whatever when I'll change the slides. my solution. All right? See that? So you've got 9 of them. Sorry, 1, 2, 3, 4, 5. Yeah, it is 9 of them, which is 250. Correct? Yeah? What happened to the rest? The rest, how much do you lose?
Negative 250.
Yeah, the player will lose 250. So ignore. I'll redo this when I upload that. So the 250 should be here and everywhere else. All right? So from there, what you could do is you could define a probability mass function. I am going to let X be the amount of winnings in a game. Alright? X is the amount of winnings in the game. And there will be only 3 situations, correct? You will only have, you lose 250, the winning is losing 250, or you win 250, or you win $10. 3 situations. Agree?
Yeah.
Okay. From there, you can write out the probability mass function. You can have the table. When x equals to minus 250, the probability of x equals to x is 26 over 36. And then 250 is 9 over 36, and $10 is 1 over 36.
You change.
Yeah?
Yep.
Got it? So from there, you can find the expected value. The expected value will tell you if you play the game consistently, keep going. Let's say if you play 10,000 times, you will expect to lose 90 cents per game in the long term. Minus 90, yep.
Do you have to do like negative 250 and like 250 10, or can you do like 0 250 12.5 for your x, like small x?
0
It doesn't matter as long as at the end you say it's
and
negative.
12.5.
It doesn't specify like what you actually have to put in the table.
If you read A, define the probability for this situation
What
and
else did you
hence state
get?
how much a player can expect to win.
You still got it right.
So if you
Yeah,
work it out
yeah.
as 0, 2.5.
If you just do 250 take the expected value, you should get the amount you lost.
Yeah, you can do that. I think. Yeah, you can do that. You can do that. Yep. It's just if you read the question, it's easier to look at the winning.
Yeah.
That's
okay.
all.
Yep.
The question is expected to win. You're not expected talking about losing.
Yeah.
So expected to win. Yeah. So expected to win. Yeah. You lost 90 cents in the long term on average. So anything to do with gambling, you can see that it's not going to be fair.
Always never fair.
So for it to be fair, the long term expectation, the mean should be 0. So you can see that if you go to casino, you will never win. You will never win in casino
All on
because
red, man.
in the long term, they want to
All
make
on
money.
red.
All right?
You double it and then you put it all on 17.
You'll never win in casino.
36x, man.
All right. So ignore this. I will redo the table.
Yeah.
Once
So
I
you're thinking,
once I
like, put
upload
in
this.
50
Ignore
bucks
that.
and
No,
Alright.
you just put all
Alright.
on red, double all your money.
Oh, yeah.
And then you
So
put it all on
this is
17.
an example that I
Easy,
want to
easy,
show you.
easy.
It's a discrete
That's how it works.
value, although it is not integer. Discrete as in you lose 250, there's nothing in between. You win 250, nothing in between, and you win $10. Alright? Alright, example 3. Example 3 deals with relative frequency. Alright? You need to think about using relative frequency here to be able to construct a probability distribution.
Don't kick it.
Right? And then you can work out part B. And you can work out the standard deviation. And then let's talk about part E. Part E is the interesting one, it's interpreting. Alright, let's start off with looking at the relative frequency. First thing, if you want to use relative frequency to find the probability mass function,
You
the
add up the
probability
total and
distribution,
you put it
you
over
got to
that
work
total.
out the sum.
Yeah.
Alright? So, working out the sum, I'm pretty sure it's 5,000.
Wow. What is that?
Yeah, work out the sum. Oh, there are things that I
Yes.
did not animate. So it's total is 5,000. So I can use the number of families, divide by 5,000 to get your probability. Alright? This is what I get. And then to work out probability of between 2 and 3, whatever it is, let me have read the question. 2 or 3 children. So 2 or 3 children is 2 between 2 and 3. So you need to include just 2 and 3, probability of 2 and probability of 3. Therefore it's 0.463. Next one, at most 2 children, given that it is known that the family has children. So you must ignore where family without children. Alright, it has to be x greater than 0 and less than or equals to 2. So therefore, the probability is 2 and 1, probability of a family with 1 children plus 1 child, and probability of family with 2 children divided by 1 minus
So you didn't
probability with no kids. Therefore 0.8921.
So isn't it greater than 2? So you have to also have 3.
At most 2 children. At most children is 1 or 2.
Oh, at most, yeah. Right.
At most. The question said at
Yeah,
most.
yeah, yeah.
Alright?
Can't it be 0 as well?
At most 2 children doesn't
They
include.
don't have children.
You have children.
Yeah.
No 0. Henry, put your phone away, please. Alright, part C. You can work out the expected value using your calculator. I assume that you know how to use your calculator. Use the step function. Can you check my answer, please? Use the step function. I'm going to give you a couple of minutes.
Keep it
Use the
moving.
step
You do
function.
this, you get better in tests.
I know how to do it already.
You know how to use the calculator
Pretty
already?
quick.
Really?
You need to use your calculator.
Right.
Who hasn't got a
Sure.
class bag?
Yeah, I got it on my iPad.
Anyone without a class bag?
Let me do it quickly. Let me finish it.
Wait, so which one is
Oh,
blue?
shit.
Which question is blue?
Part C.
Come and get a class bag from me if you haven't got one.
It's 2.
Alright? So you must be able to use your class bag.
2. It's 1 kid. 1.463 kids.
Class bag.
1.463 kids. I reckon.
I missed one.
You should have least 1 and least 2. So x will be your least 1.
1.463.
Y will be probability
Yeah.
will be your least 2.
Which is 250.
Alright? So and you go to calc
But it's not uniform.
Yeah.
Okay.
and then one variable
This adds up to
and then you go to x
Sure.
least is least 1.
260.
yeah.
Frequency is least 2.
1 kid.
Alright, that's your probability. And you should come up with the same answer as I do.
Because 2
Wait,
Which
what's
is-
it? Is it standard D?
Yeah.
Or what is
is
it?
265.
Alright?
I got different.
Do you get what I'm saying?
Got the same answer?
Nah.
Or some of you are still using
Yeah, I know
your
what you're
phone.
trying to do. Yeah, you're trying to like use the on the ends of the average.
Yeah?
See how.
Wait, let me see.
smooth it
What's one?
is.
So once you've done that,
Oh, you couldn't even do it.
now it says there answer to the nearest whole.
1.
So it has to be the number, 1 child on average.
Graph the probabilities.
Yeah.
Bro, told
So-
you this is gonna improve your exam.
That shows how you did.
And then calculate the standard deviation. You
Yes.
got it from the calculator straight away.
X and then probability.
Alright?
One variable.
Now, the next thing that I want to ask you, a second region, look at E. A second region was surveyed and was found to have a mean of approximately 1.5 times the mean of the previous region.
What happened?
If Y is the number of children per family in the region, do you think expected value of Y equals to 1.5 expected of value of X implies that Y equals to 1.5X?
Wait, let's see this.
Do you think that's the case? Do you think statement E is correct?
No.
Yes, it is correct, I think.
You think it's correct? How many say it's
Actually,
correct?
no,
How
actually,
many
no,
think
no,
it's
no, no,
correct?
no, it's not. No, it's not.
It's no, it's not.
Because it could be plus. It could plus. Like if you have.
It says that it's approximately the expected of value. Let's compare Perth and maybe Adelaide. All right.
Yeah.
So this value, expected value for Perth is 1.463 or 1.4.
Yeah.
All right. Expected value of Adelaide is 1.5 times that.
Yeah. Yeah.
All right. But does it mean that the population of Adelaide is y? It's 1.5 of x.
No.
It's not, because
Could
it
plus.
is not.
Could be just like a translation, not a dilation.
You don't even have to be translation, because if you think about it, the spread of this 0 to 1.5, all right, because you're looking at relative probability, you could still have something which is not like this, but the expected value could be the expected value of y, the average or the expected value of in Adelaide, let's say in Adelaide, could be 1.5, but it does not necessarily translate to y equals to 1.5x. All right, you could have numbers that will give you the average of 2.1945, but y does not necessarily be equals to 1.5.
So if y equal to 1.5x,
Expected of y is 1.5x, is y equals to 1.5x, not necessarily
like
true.
what if it actually was 1.5x, would the probabilities, would the small x's be 1.5 times the x's originally?
If the statement say y is equals 1.5x,
Yeah.
then e is definitely 1.5 ex. Ey is definitely 1.5 ex.
Yeah, but say would like 1 go to 1.5? Like the small, is that what it means when it says that?
Okay, so what it means, the question said, all right?
I mean, like if it was y equals to 1.5x.
Okay, now let's look at it. Ey is 1.5 ex. All right?
Yeah.
That's what we're looking at.
Yeah.
This is given, the statement. Now, we can have y, and this is probability of y equals to small y. All right, 0, 1, 2, 3, 4, 5.
Yeah.
Yeah? All right? So you know that Ey is that times that, that's the, okay.
Yeah.
So is it necessarily this? Will it always be 1.5 times this? Or 1.5 times this? 1.5 times that? Because, oh sorry, this, wrong. My fault. Okay, so y, 0, 1, 2, 3, 4, 5, and probability of y equals to y. Alright? So you're thinking about whether the expected value of y, sigma y times probability of y equals to y. Alright, you know that that's given as 1.5 expected value of x. However, what happened is, can we say that y is actually 1.5x? Can we actually use this information and change it to 1.5x? 3, 4.5, 6, and that's 0, sorry.
Yeah. Oh, so that's what it means.
And
So
whatever.
you time
Yeah.
the small x by 1.5.
Yeah,
Okay,
1.5.
that's what it means, okay.
But no, it is not true,
Yeah.
because you don't know what the relative frequency is here.
yeah, of course. Yeah.
You could come out with a value. You could work out to be 2.1945.
Yep.
But the relative frequency, unless the relative frequency of that particular region is the same as the previous region, if not, it's not right.
Yep.
All right. All right. Last example. During the late 1940s, an experiment with a particular strain of the myosma virus was conducted on 3 healthy rabbits. Each of these rabbits were exposed to the virus, and they were observed to see if they survived or did not survive. it was found that the probability of the first rabbit surviving was 0.5. The probability of second rabbit surviving was 0.4, and the probability of the third surviving was 0.3. Construct a probability distribution for the number of surviving rabbits out. Hence, work out the probabilities.
They don't add
Now,
up.
using the strain of virus, comment on the expected survival rate as a percentage. So I'm going to start off asking you, how are you going to construct a probability distribution table?
Define it.
3 diagrams. Yes, 3 diagrams
Why?
because you've got 3 rabbits. You can start off with the first rabbit, 0.5, survive and did not survive, S and S bar. Rabbit number 1, 0.5 and 0.5. Rabbit number 2, 0.4 and 0.6. So the situation is rabbit number 1 survived or did not survive. Alright, if it survived. Now let's have a look at rabbit number 2. Rabbit number 2, probability of surviving is 0.4 and 0.6. S and S bar. S and S bar. 0.4 and 0.6. Yeah? And then look at the third rabbit. S and S bar again. But this time the probability is different. It's 0.3, 0.7, 0.3, 0.7, 0.3, 0.7, 0.3, 0.7. So use your tree. You are going to use your tree to decide how are you going to draw the how are you to construct the probability distribution. So here, what I've done is I wrote down 3 survive, the number of surviving rabbits, 3 survive, 2 survive, 2 survive, 1, 2, 1, 1 and 0. So it's very clear, I know that this will be all 3 rabbits survive. This situation, 3 of these will be 2 rabbits survive, 2 rabbits survive, 2 rabbits survive, and 1, 1, 1, and then everyone did not survive. Yeah? So, you can work out the probability. Use your calculator. Draw the tree, look at the situation. You know that this is non-uniform. Look at the situation, and then you can work out the probability. You can sum the probability of 3, sum the probability of 2, sum the probability of 1, and sum the probability of 0. Correct? Yeah? Do that first. Once when you're asked to construct a probability distribution, important thing is look at this, the tree diagram, and work out how many will survive, how many did not.
Galen, wake up.
Once you've done that, you should be able to construct probability distribution. Agree? So the probability distribution is something like this. Sum R equals to 0, 1, 2, 3. 0 survive, 1 survive, 2 survive, and 3 survive.
Lit.
And therefore, this is your probability distribution. And then you can work out the rest, like probability of R less than 3. Now, question 2 is interesting. Question B2. If you talk about probability of R equals to 1.5, exactly 1.5, is it there?
No.
In that table?
No.
No. Therefore,
I'll
2
do
is
1.
0. Alright? That 1 less than 3. Survive. 1 take away 0.06. Because it's less than 3, you want this bit. 0, 1 or 2. And therefore, it's 0.74. But there's nothing in between. There is not possible to have 1.5 rabbits survive. Yeah? It's not possible to have 1.5 rabbits survive.
But I thought you said like you can round it up.
This one, look at the sign, equals 1.5. You can't round. No, it's exactly. Unless it is greater than equals to. This is
Oh,
exactly 1.5.
So if it's greater than or equal to, you round up.
Yes.
We'll round to the.
Yeah, now it's less than. Yeah. Alright, which is the next situation, less than 1.5. You round it down to R equals to 1 and R equals to 0.
Okay. Yeah.
Yeah?
Yeah.
Got it? Part 2 is exactly 1.5, which it does not occur. It will not occur. Part 3 is less than 1.5.
What if one's like
So it could be
brain dead?
1 or 0. So the difference, you need
Yeah.
to be able to understand the difference. Exactly, there will be no exactly 1.5 rabbits survive.
Wait, so for the third part, if it was like 1.9, would it still round to 1?
Yes, because it's less than 1.5, it's
Yeah,
not
okay.
greater than 1.9.
Yeah.
Alright? Less than, therefore round to 1 and 0.
Yep.
You're looking at anything which is less than 1.5 here.
Yep.
So 1.5 is somewhere here, is anything less than that.
Yep. Because that's like the only ones you can guarantee that are less than 1.5, right?
Yeah, that's
Yeah,
right.
yeah.
That's correct. That's correct. That's correct. That's correct. So the last bit, use the strain of the virus, comment on the expected survival rate as a percentage. So what you need to do is work out the expected value. So the expected value is 0 times 0.21, 1 times 0.44, and so on and so forth. Alright? You can use that method or you can use your calculator to work out. It's up to you, it really doesn't matter. Both ways you have to use your calculator anyway. And it becomes 1.2. Alright? So 1.2 divided by 3 because you've got 3 rabbits times 100%, 40%. So therefore, it is 40% survival rate. So the expected value, you think about it, you will, if it is not rabbit, you're thinking about 1.2. Alright? And then from there you can work out, you know there are only 3 rabbits. 1.2 divided by 3 times 100%, therefore it's 40%. And that's 40% survival rate. Alright, I'm finished for the day. So you've got a few more exercises that you can do.